Okay, so this is problem number 66 on chapter 1 that I did. Air is blown into a spherical balloon so that when its radius is 6.5 centimeters, its radius is increasing at 0.9 centimeters. Find the rate at which the volume of the balloon is increasing. So basically, I got the radius and the derivative of the radius, and I did the derivative. And with the volume of the balloon, obviously, I got that that equation, and then I plugged in the radius right here, and with the derivative, and that gave me my value at the rate at which the volume of the balloon was increasing. So for B, it was if this in volume flow rate of air entering the balloon is constant, at what rate will the radius be increasing when the radius is 0? So basically, I took that value and then I did the derivative again, and then I plugged that value in for the radius, the 13 in for the radius, and then I took the derivative, the derivative of the volume, which I got in A, and I put it on the top. So that's why I got 4 pi r squared, and then the derivative of the volume equals 0.23 centimeters per second. So that, and then I just said the change in the rate of the radius at 13 centimeters, which is what we used for the radius, is 23 centimeters per second. And then for C was explained physically why the answer to part B is larger or smaller than 0.9 centimeters per second if it is different. And it was different. It was 0.23 centimeters per second. So when the radius was 6.5 centimeters in A, we enter the same volume of air in 1 second, but it is spreading over a small region. Changing rate of radius is faster. Volume increases as radius does. And then the changing rate of the radius was slower. Okay, so for this one, we had Given's acceleration equals 0.1 meters per second. The initial velocity equals 0 meters per second, and then the second acceleration equals negative 0.5 meters per second squared, and and then the velocity final for 2 equals 0 because it stops, and then the velocity initial, the second velocity initial equals the velocity final because that's like the same. The velocities are equal as the train is going. So then the change in the equations we used were these change in x, vxi, change in t plus 0.5 ax, change in time squared, velocity x f equals vxi plus acceleration in the x direction, and then the change in time, and then velocity x final, and then velocity x initial squared plus 2ax change in position. And then basically I used the first one. Immediately, and then I plugged in 0. I got 0 for the first part of it, and then 0.5 times 0.1, which is what we used for the first acceleration. So, and change in t 1 squared, and then you multiply that, and then you get 0.05 change in t squared, and then the velocity final equals, I did that one next, and then you plug in what you know, and then it got 0.1 for the acceleration right there, and then that's the velocity 2. So you have the change in position 1 and the velocity 2, and then you go to your third equation, which was the velocity of you got the velocity, and then that equals the first the second velocity initial change in t plus 2, and then the acceleration of 2, change in x 2, change in x, it equaled 0.01 change in t squared, and then yeah, that one. Okay, and then I took those two values that I knew that I got in earlier equations, and then I equaled them to 1,000 meters, and then I got 0.06 change in t squared, and then I got a value for t1, which was 129 seconds and change in time. So I had to convert it to meters per second for the initial velocity for the second part. So then I did 0.1 times 129 equals 12.9 meters per second. And then for this part, you get 12.9 meters per second minus 0.5 meters per second squared. That was the acceleration, and then that is the velocity. So right here, I'm trying to find the change in time for the second part. And then I added it to the other side, and then I divided it. So then I got 12.9 meters per second over 0.5 meters per second squared, which I got 25.8 seconds. And then the change in time equals change in time 1 plus change in time 2, so it equals 129 plus the value we just got, 25.8, equals 154.8 seconds, which equals the change in time for the whole thing. Okay, so for chapter 3, I did problem 8. Vector A has a magnitude of 29 units and points in the positive y direction when vector B is added to A. The resultant vector A plus B points in the negative y direction with a magnitude of 14 units. Find the magnitude and direction of B. So in this problem, we're given 29 units. So I used A equals 29 j hat, and then I subtracted A from R to find B. So then I did that, and I got what R equals negative 14 j hat, and then B equals R minus A. That's finding B. And then we already had the fact that the vector of A equals 29 joule j hat. So it was minus 14 minus negative 14 minus 29 equals negative 43 j hat. So B is 43 units in magnitude, pointing in the negative y direction for that one. Okay, so for chapter 4, I did number 12. An astronaut on a strange planet finds that she can jump a maximum horizontal distance of 15 meters if her initial speed is 30 meters per second. What is the free fall acceleration on the planet? So I had the givens, radius equals 15 meters, velocity initial is 3 meters, and I got theta max equals 45 degrees, and then I used an equation to find free fall. So I got R equals VI squared sine 2 theta over gravity, and then I changed the g because we're finding gravity in this, because we're trying to find the free fall acceleration on the planet. So then I got velocity initial squared sine 2 theta all over r, and then I basically just plugged in like the givens that I was given. So, and I got 0.6 meters per second squared equals the acceleration or the gravity on that planet. So for chapter 5, I did number 14. A brick of mass m has been placed on a rubber cushion of mass m. Together they are sliding to the right at a constant velocity on an ice-covered parking lot. Draw a free body diagram of the brick and identify each force acting on it. Draw a free body diagram of the cushion, and then identify all action-reaction pairs of the forces in the brick, cushion, planet system. So for A, I drew this. There's a normal force acting on the brick by the Earth and the cushion pushing up on the brick, and then there's gravity pushing it down. For the cushion, it's sliding on the ice, so there is a little bit of a force of kinetic friction, and then as it's moving, and then there's a normal force pushing up, the Earth pushing up on it, and then the brick is pushing down on it, and the gravity is pushing down on it. So for C, I said basically just explain what I just did, which is the same kind of thing, but there is a gravitational force exerted by the brick on the Earth and the Earth on the brick. There is a gravitational force exerted by Earth on cushion, cushion on Earth. There is a normal force exerted by the brick on cushion, cushion on brick. There's a normal force exerted by ice on the cushion, and a force exerted by the cushion on the ice. So yeah. For chapter 6, I did number 13. So number 13 was a hawk flies in a horizontal arc of radius 12 meters at constant speed, 4 meters per second. Find its centripetal acceleration. And so for that, I did use the formula AC equals V squared over R. So R equaled 12, that was given to us, 12 meters, and then velocity equaled 4 meters per second. So I just plugged it in, got 1.33 meters per second. And then for B, we were asked it continues to fly along the same horizontal arc, but it increases at the rate of 1.2 meters per second. So find the acceleration, magnitude, and direction in this situation. At the moment, the Hawk speed is 4 meters. So then I use like Pythagorean theorem here, and the tangential acceleration plus the centripetal acceleration. So we're given the tangential, so I just plugged that in, and then I plugged in the centripetal too and squared them both, and then I got this, and which was 1.79 meters per second squared for B. And then we were asked to find the angle. So I used the formula theta equals tan to the negative 1 AC, the centripetal acceleration over the tangential, and then I just plugged it in and got 48 degrees at 48 degrees and 1.79 meters per second squared. Okay, for chapter 7, I did number 21. A light spring with spring constant K1 is hung from an elevated support. From its lower end, a second light spring is hung, which has spring constant K2. An object of mass m is hung at rest from lower end of the second spring. Find the total extension distance of the pair of springs. So I equaled the force of gravity to the spring force for both of the spring constants, and then I got for each of the distances, and then that got me the distance, the total extension. And then to find the spring constant for B, I just moved the pieces around, and then I got K equals K1, K2, all over K1 plus K2, and that was the spring constant, to find the spring constant of the two.